my name is Carmina. I'll be your host for today's virtual seminar, Robust Design Workflow for Signal Integrity, brought to you by Keysight Technologies. Joining us today is Tim Wang Lee. Tim is a signal integrity application scientist in the Pathway Design Group of Keysight Technologies. Tim is also a PhD candidate concentrating on signal integrity simulation and measurement correlation at the University of Colorado Boulder. I first met Tim years ago at DesignCon. I'm very happy to have him as one of my colleagues. Typically, we sit across from one another at the headquarters in Santa Rosa, so it's good to see his smiling face today. Welcome all. Tim, you now have the floor.
Thank you, Carmina. So today what we're going to be talking about is robust design workflow for signal integrity. Now I want to introduce you to two engineers. One engineer is Tread and his traditional design approach. Looking from the left, create design based on vendor guidance. And in the middle, then Tread goes to fabricate the prototype, then measure and verify the performance. Now, if I were to score Tread's approach, the practicality is at 5. And effort, about 2, low effort. And troubleshooting, it's a little bit hard at 3 because you really need the experience, right? Then the what-if analysis, it's a low 1 right there. It's really hard to do a what-if analysis with Tread's approach. So here's a summary. It's easy to fabricate, but you need experience and it's difficult to perform what-if analysis. Now let's take a look at Rob and his virtual design prototype robust approach. Rob starts with a virtual design prototype, simulates and validates the prototype, fabricate the prototype, then measure and verify performance. If we compare the scores, the practicality, I would say, is actually off the charts here, but let's cap it at 5. The effort needed to create such an approach is a bit higher at around 3, but what's astounding is the troubleshooting goes off the chart as well at 5 and what-if analysis. And here's a punchline. You invest a little more time ahead of time and get a lot in return. And today, what we're going to be looking at is the robust design workflow for signal integrity. It looks something like this. You start with rule of thumb estimations, create some virtual prototype with modeling. You go through your 3D EM extraction, and finally, you can perform some analysis. We'll see how everything plays together with eye diagrams, mixed mode S parameter, time domain reflectometry, and single pulse response. Today, I want to focus on one thing, and one important thing is anticipate before you simulate. A lot of people are just pressing the simulate button and see what happens. That is a dangerous approach to simulation. It's not safe. And today, we're going to practice safe simulation, anticipate before you simulate. Now here we're going to go through an example design problem for USB serial link. A little more detail on the link will be concluded. And then we're going to start with some rule of thumb estimations to virtual prototype. In the process, we will answer 3 big questions. What I metric should I follow? How long can my differential traces be? And what trace width should I expect with my stack up? Going through these 3 questions, we'll have 5 rule of thumbs. And at the end, I'll have a cheat sheet for you and a challenge. So make sure you stay till the end to accept the challenge. And after all this, the virtual prototype is created. We will take a step further and compare our design to a real fabricated board. That's where I'll show you how the virtual prototype and the 3D EM simulation, SI Pro, can create a virtuous cycle where it's very easy to do troubleshooting, what-if analysis, and design explorations. Without further ado, let's take the first question. All right, so here is our design problem. We have a USB connector to U1. We're going to ask the big questions. Given the constraints here, our TX is running at a 5 gigabit per second with an RX at U1. The questions are, number 1, what I metric should I follow? Now, my first answer to this question is, well, you can just pull up the standards and see what it says, right? Sure, that's doable. But if you look a little closer, you see the box in here. Here is what we're looking for. And there are a lot of notes And the note says, well, it's measured after receiver equalization function. Well, what are we going to do? We barely have a channel. How are we going to decide what equalization to use? The punchline here is it's great that the standard provides some kind of information for testing, but it's kind of hard to design with the texting specs. That's why we're going to have our first rule for estimating loss and I without EQ. That's A73, A73, A73 rule. A standing for 8 dB of loss at the Nyquist frequency, which is half the data rate at NRZ. 7, a 75% UI I width, 25% jitter, and 30% of eye height. That's 873. How does it look like graphically? It looks like this. If you normalize the frequency to the Nyquist frequency, at 1, you see 8 dB. And the eye should look something like this. The dark blue lines is the ideal eye opening. And in the middle is with 8 dB of loss at Nyquist, a typical channel. Now, given our setup, TX at 5 gigabit per second, 25 gigahertz, and rise time 15 picosecond, here is what we see with A73 rule. 8 dB of loss, 75% UI, and 30% eye height. So very similar to what we expect. You see this, the rise time, and you have right here is 75% of the UI. And on top, eye height, you have about 30%. Now, the question we're going to ask is, well, how does it look like compared to the standards requirement after EQ? If we put the mask in red in the middle of the chart, the plot, we can see that the eye mask for standard is fitting pretty loosely in the middle of the eye. What can we use this margin for is things like reflection noise, random jitter, and other deterministic jitter, and other source of impairments. Good. We answer our first question. What eye metric should I follow? On the left here, I said A73, 8 dB of loss, 75% UI, and 30% eye height at the receiver. Next question is, how long can my differential traces be? To solve that mystery, we're going to take a look at a 50 ohm transmission line that is 10 inch. That is 10. This is a measurement of that 10-inch line, de-embedded. So there's only the traces we're looking at. Now, if we want to look at the per inch per gigahertz metric, what we need to do is divide this curve by 10, because it's 10 inches, and divide it through our frequency. And what we find is this. Well, if you look at it, I put a little dotted line over there. That's at 0.1 dB loss per inch per gigahertz. That is crazy how flat it is as you go higher and higher frequency. It remains at around 0.1. So this is a real measurement. It's about 0.1. And just to take care of the range of different substrates and conductor loss and dielectric loss, I'm going to put it 0.1 to 0.2 dB of loss per inch per gigahertz. That's our estimation rule of thumb. Now, if we combine the 8 dB, 7%, 30% rule with 0.1, 0.2 dB, we'll do a little quick calculation at our 5 gigabit per second channel. It's a 16 inch. We'll put it here, 16 inch to have 8 dB loss, a Nyquist of 2.5 gigahertz. On the graph, at 5 gigabit per second, 16 inch, it looks right here. That's it up. Now, if we increase the data rate and while maintaining the same metric A73, we will see the plot that goes like this. As we go up in frequency, the length we can tolerate at 8 dB of loss is a lot less. It's decreasing. So here's the punchline. This is the reason why there are more signal integrity problems with longer lines at higher data rates. Because given 0.1 dB per inch per gigahertz of loss, at 30 gigabit per second, you can only have less than 4 inches of trace to have 8 dB of loss. After answering this question, using 0.2 2 dB of loss per inch per gigahertz, we're going to take a look at question number 3. What trace width should I expect with my stack up? Now, I know you're thinking, well, Tim, we have to start with a stack up, right? You are completely correct. We have to start with something. So here is a 20-layer stack up. 8, 9, 10, 11, 12, 20, 8, 16 to 20. We're going to take a closer look at the top layer, the microstrip layer. All right. Now, if I tell you the trace width is 6 mils and the substrate height is 3.5 mils, I'm going to do a quick poll here. What do we think the impedance is going to be? Is it going to be, number 1, 30 ohms, 2, 50 ohms, number 3, 75 ohm, or number 4, I need a field solver? So I will start the poll right now, and you have a minute to answer the question. I'm going to wrap up the survey and move forward to our result. Wow, this is very cool. All right, about 23% says 30 ohms, about 38% says 50, 10% says 75, and about 3% says I need a field solver. All right. Well, it's a rule of thumb, so I'm going to give you a quick estimate here. The answer is 50 ohms. The answer is 50 ohms. The rule of thumb is if it's a single-ended microstrip transmission line, the impedance rule of thumb goes like this. If the width over height is about 2, the impedance is about 50 ohms. And we'll see a demo of a 2D field solver that actually illustrate this rule of thumb later on. So just remember W over H is 2, 50 ohms for a microstrip in FR4. Now next is the differential impedance, because USB needs differential traces, differential signaling. So first, I'm going to summarize what we did before. The single-ended microstrip impedance rule of thumb, width over height is 2. The single-ended impedance is 50 ohms. Now if I have a edge-coupled microstrip line, given that the traces are still 6 mils, the height is still 3.5, both of them, and the spacing is 18 mils. Now another poll question is going to come up and ask you whether it is the differential impedance is 88.8 ohms, oddly specific, or 100 ohm, 75 ohm, or same answer, I need a field solver. Okay, here are the results. About 10% says 88.8 ohms. About 70%, the majority says about 100 ohms. That's great. It is about 100 ohms. The answer is about 100 ohms. Instead, I have 8.275, and 10% says I need a field solver. But the answer is 100 ohms. Here, the punchline is the differential impedance of microstrip diff pair. The rule of thumb is when the spacing is 3 times of the trace width. That means that these two traces are uncoupled. The differential impedance is going to be twice of that single-ended, which is about 50 ohms. Moving on, so we have the microstrip line, but we want to also look at the strip line impedance. Well, similar exercise here, but we do have a substrate height from the top and the bottom, so they might be of different height. Now, the rule of thumb here is when the width over height, the smaller one is 1, the single-ended impedance is going to be about 50. The reason why I take the smaller one is because most of the field lines are going to be concentrated within that region. When it's very close, the traces are the signal and the return are very close to each other. Similar idea for the microstrip line. The rule of thumb for differential line and strip line is also 3 times the trace width. So we can see here, if my 50 ohm line single-ended is 3 mil, given the substrate, we have 2 single-ended lines with a 9 mil, that's 3 times the trace width, that would give us about 100 ohms. Now here's another question that we're going to ask. What would happen if I don't have enough space for 9 mils? What if I move the traces a little bit closer? What do we expect the differential impedance to do? Is it going to increase, decrease, stay the same? Or 4, I need a field solver. Okay, now by this time, this third question, we should be clear that this is a rule of thumb, and let's not pick 4. All right, let's not pick 4. Let's pick between 1, 2, and 3. And in 5, 4, 3, 2, 1, go. Question is again, when I decrease the spacing of a differential pair, the differential impedance should A, increase, decrease, stay the same, or I need a field solver. You can pick anything but 4. Let's not pick 4 today, or right now. This is the exercise that we're going to go through is, once we have these rule of thumb in mind, it will be very easy to estimate what you expect in terms of impedance, higher or lower, reference to 50 ohm. Because sometimes you don't always have the time to bust out your 2D or 3D field solver to put in the numbers and create a mesh and do a simulation and analysis. That will probably take 30 minutes to an hour. But with the power of rule of thumb, taking width over height, that will be a 5-second, 10-second kind of idea. You get a really quick estimate and rough idea of, okay, this trace look close to or not close to 50 ohms at all, given the geometry. I'm seeing good results. We have nobody picking the field solver, 0.0%. I'm really proud. I'm really proud. That's great. Okay, we got a couple saying stayed the same. Increases and decreases. All right. Okay, give you 5 more seconds to vote. And we'll see what the majority is saying. Give me 5 seconds. 4, 3, 2, 1. Great. Here are the results. About 25% says increases, about 70% says decreases, about 3% says stay the same. Nobody says I need a field solver. Great. So this is what we want to see is we want to be able to have a kind of idea of what it's going to do before we put in the field solver. The answer here is decreases, because when we put the traces together, the mutual capacitance is increasing, so differential impedance decreases, as shown here in the slide. All right, now let's take a step back of all the fun we had and see where we are with the design problem. We asked the 3 big questions. What I metric should I follow? How long can my trace be? And the width for the stack up. So we answer all these questions over here. Now I'm going to give you a demo on how one would do it in ADS, especially in CILD, Controlled Impedance Line Designer, and how we can use the transmission line we have designed, a virtual prototype, and put it back into our TX and RX simulation and see what the eye would look like. Right? So I'm going to start a demo video, and we will see what we can do with CILD, the Controlled Impedance Line Designer.
We'll start with a substrate editor. We'll find CILD over here, and that stands for Controlled Impedance Line Designer. Now if I scroll in a little bit to the substrate, I can find the substrate height to be 3.5 mils. And to get about 50 ohms, I need the width to be 7 mils, which is what I put here. And after I hit simulate, I should expect the impedance to be close to 50. 46 right there, right on. Now let's look at another example. Looking at this one, once I have everything configured, I can save this configuration of transmission line. Then I can pop that right in, Control V, into my channel simulation.
Once we pop in that channel, and I put it at 16-inch as we can see here, and that is the differential strip line that we designed with 393 uncoupled, about 100 ohms. Now we saw in the demo that I saw the trace height, or the substrate height, is 3.5 mils, and I know what multiplied by 2, that's 7, and that gives me 46 of single-ended impedance, and that is powerful. Within 5 seconds, I know what to expect. See, 5 ohms out of 50 without any major work. That is very astounding. You can use that rule of thumb everywhere, and it's very easy to use. But let's take a look at the channel simulation that we did with our virtual channel. We designed a 16-inch using the using the 873 rule. We're gonna send in a 5 gigabit per second from the transmitter. And we should expect, basing on what our 873 rule, the eye should be pretty open compared to the mask, which is shown here. We can see that although the 16-inch doesn't give us really 75%, well, it's kind of close. We have 86% of the horizontal eye. How about the vertical? The vertical, we have 38%. So this is how everything's working together, all the way from rule of thumb to 2D virtual prototyping. Everything's working consistently together. We can see how everything's connected, and we are getting what we expect. So we have confidence to build on what we know. Next, we're going to take a step further, compare our design to a real fabricated board. As shown here, this is a Xilinx board that they are great to share with us. We're going to take a look at how they design their USB traces, given the same location of the receiver and transmitter over here, and to taking a board layout file into a 3D view, we will use SI Pro. Everything's included within the same ADS environment, but SI Pro stands for Signal Integrity Professional. It helps you quickly take your board file, be it BRD, Gerber file, or ODB++. We can take that in, import it, and take a look at a 3D view of your board and extract the 3D EM simulation and use that result into the channel simulation. So we'll take a look at another demo video with SI Pro, and we will come back to look at what we expect from the traces.
We'll start with ADS window, the main window. To import a file, I'll go to File and then navigate down to Import and find Design. We'll start with ADS window, the main window. To import a file, I'll go to File, navigate down to Import, find Design. Design the window will pop up. Here's where you can use BRD files or Gerber. Once you choose the file type and the right path, click OK. It will start the layout window.
Hey, Tim.
To the import. To start PI Pro, go straight to the icon right there. Click on it and click on it.
Hey, Tim, it's Carmina.
Once the layout import is done,
You want us?
SI Pro window will show up, as well as a 3D view of the board. You can do it different ways. You can look at the trace, the USB trace in the middle. Deactivate the components, and just show only the trace. And here are the other layers. You can zoom in and zoom out. And here is what it looks like with only components.
happening at once. It's like talking to three Tims, give you more signal integrity knowledge altogether.
I was just about to say, we were like, there's a double audio, so, but it's a good video.
It's good, and I promise the video by itself has only one voice. We'll send that out later, but just to conclude here, I was showing you how to import a board and look at the trace we want to simulate, which is the USB trace shown here on the design here. On the left, we want to see, is it consistent with what we expect? You have the TX is 5 gigabit per second, Nyquist 2.5, and then the length is 7-inch. We don't want to just say, let's do it. Let's see what happens. We know the rule of thumb now. We can put in the numbers. We're given 0.1, 0.2 dB per inch per gigahertz. We can take a step and look at what we know. We know the length is 7-inch, and what we expect is the loss at Nyquist is about 1.75 dB to 3.5. That's twice. So the rule of thumb is down there. So this is how we're going to use it. On the right, I'm going to show what we expect is STD21, differential insertion loss, versus frequency. This is the line we expect. Is we have a Nyquist at 2.5, loss between 1.75 to 3.5 dB. Now let's see what the 3D extraction shows. On the right, I've said we expect loss to be between 1.75 to 3.5, and here it is. At 2.5 gigahertz, the Nyquist frequency, the simulation shows minus 3 dB, which is really within our expectation. It's great. But is it? Now, the skeptics out there would say, well, Tim, you promised us a straight line all the way through 15 gigahertz. What is this thing I'm seeing at 10 gigahertz? Well, I'm asking myself the same question. What is happening at 10 gigahertz? So this is what we're going to take a segue to how we can create a virtual simulation cycle. We had the virtual prototype, and we did the 3D EM extraction. Now we'll see how these two play really well together, because we had a different result that we see. We expected a straight line, but we saw a little dip at 10 gigahertz. Let's see if we can, number one, troubleshoot this issue. First, we're going to take a closer look at the connection over here, close to the USB to the RX. I'm going to take a closer look at this area. If I zoom in, I will see a ESD diode right there. If I remove all the components, I will see that, wow, there is about 0.15 inches of that transmission line there. What is that going to do? Well, let's take a look. That's the top view of what it looks like symbolically. The length is about 150 mils, 0.15 inch. If we do a little quick calculation using length and frequency and propagation speed in FR4, we find that the resonant frequency of this stub is 1.5 over the length in inches. If we put in the numbers, it's about 10 gigahertz. Just a side note, this estimation is also great for vias. If you have a via that is about 150 mils, 0.15, you will also see that resonance at 10 gigahertz. Well, what are we going to do with this information? We're going to add in. So in the middle here, in the horizontal, is our 7-inch channel. And we're going to add onto it this little stub right here, hanging out 150 mil. We'll see if that predicts what we see in the 3D extraction. So here is what we're going to look at. Without anything, without the stubs hanging out, we have a straight line. If we include this pad that's hanging out, which is shown here, bam, right there. Around 10 gigahertz, we see that dip. This is a very good test and very warm feeling that tells me, well, I know that this 10 gigahertz resonance here is created by this trace that I'm connecting the USB signal trace to the ESD diodes. So that's what's happening here. So we know how to troubleshoot it, but let's take another look. So we've been in frequency domain for a little while. Let's take a walk in the time domain, where we'll use time domain reflectometry to look at the same trace, looking at it from this angle. Now, if the pad is really there, we should expect a low impedance because we have 100 ohm differential coming in and it's splitting up into two different branches. So that should be a low impedance. And lo and behold, we have a TDR plot, and right there we have a lower impedance looking into at that point. Another thing to note is, well, the rest of the trace pretty uniform. You see all these bends, it's all right. You have around 95 ohms of trace right there in the 3D, from the 3D simulation. Our next thing is, what have we done? Let's see. We have used the rule of thumb to did a quick estimate and you look at the 3D extraction of the board. And given that the board has 6-7 inches of trace on it, we expect the loss at Nyquist should be okay, which was the case. But the question now is, what is this resonance going to do to our eye diagram? Is it going to destroy the eye diagram? What is it going to do? Before we do that, based on our A73 rule, we did not specify what happens when you see a dip. But with this, only thing we specified was Nyquist. And we'll see the value of that when we put in our channel with the TX and RX. So this is what's going to happen. We're going to put in this channel. And we should expect the eye should be open based on A73 rule. Sure enough, the eye is still open based on the A73 because we specify the A73 rule, the A dB of loss is at Nyquist. And we are within that limit. So the eye should still be open. But what we observe is all these reflection noises coming from the impedance mismatch going up to the dip. Next, what we're going to show is the second thing out of the Virtuous simulation cycle, the what-if analysis that we can do. Just to recap, we use a virtual prototype to perform an eye simulation. Now let's ask the question, what if we add jitter into the system? Specifically, if I just add up, say, 0.04 UI of jitter, random jitter at TX, how would what would I look like? It's going to be close, but how much? How close is it going to get to the mask? Here it is. We see a very, very pronounced random jitter coming in from the transitions. That's expected. On the next thing we're going to look is the eye mask. The contour at BR rate is specified by the standard is 1e to the minus 12. And there it is, very close. We're super close to the eye mask. And personally, I do not feel comfortable with this. And let's take a look if we can do something about it. Using this virtual cycle again, look at the design exploration. We're going to explore the design. The final thing we're going to do is use the single pulse response to understand the channel. We have the channel right in the middle. On the left here, we're going to send in the single pulse with specific rise time and data rate. And out comes the single pulse response. Given this loss characteristic, STD21, our single pulse response look like this. If we were mark the maximum as the cursor and using unit intervals as the counting metric, then we can count whatever is coming before as the precursor and whatever is coming after as the post cursor. Now this approach is great to find numbers of taps needed for FFE or DFE. Whenever you have a transmission line and a receiver that's able to take in FFE or DFE, this is a great way to identify the number of taps that's needed. So here the post cursor, I see the major one is the first one, the second and third maybe, but I would not choose 6 for this single pulse response. Next, we'll take a look at single pulse response how it helps us understand the CTLE, continuous time linear equalization from the USB 3.0 standard. So here's the standard, and let's see what happens. Oh wait, my slides is reminding me I have to anticipate before I simulate. Looking at this frequency response, I would anticipate that low frequency close to DC will have some loss. That means I'm going to have the horizontal line is going to be a little increased. Well, if I'm negative, right, it's going to be, the amplitude is going to be decreased. But in the meanwhile, I have more than 0 dB of gain, of loss, which means we have some gain at close to Nyquist. So the peak of that single pulse should be higher. Now, after we anticipate, we can move forward, and here it is. As we anticipated, the pink is before, the black is after. From the pink to the black, we see the amplitude is decreased, and the peak, the cursor, has increased because of our about 3 dB gain close to Nyquist. So everything is consistent with what we expect. And if we look at the eye, before CTLE is very close to the eye mask, we should expect after we apply the CTLE, the eye to be open. And sure enough, the eye is open after CTLE, both horizontally and vertically. So that concluded the virtual cycle created by the virtual prototype and 3D EM extraction. And that really helps us to troubleshoot, to do a what-if analysis, and to do design exploration. Now we're at the time where we do a quick summary of the robust design workflow. What we did today was starting with a rule of thumb estimations. Using those rule of thumb, we had a great idea of where to start. And at the end, we were able to model a virtual channel, create a virtual prototype to help us understand and model the channel. After that, we looked at the layout. After the layout, we did some 3D extraction. And between the virtual prototype and the 3D EM extraction, we saw this behavior of virtuous cycle, where once we know one and the other, it's very easy to perform what-if analysis, troubleshooting, and do design exploration. And in the process, we looked at eye diagram, mixed mode S parameters, TDR, and single pulse response. But I want to take a step back and take a look at the bigger picture. Oh, see, my slides is reminding me again, anticipate before you simulate. That is the important thing today, too, is that not just pressing the simulate button is important, it's the anticipation that comes before it. Now, going back to the big picture, not only it is important to establish a robust design workflow, we have to link that to the measurement. We have created a rule of thumb world with modeling and virtual prototype, and we'll look at the 3D extraction. But in the real world lives that measurement and the real board. What we need to do is connect those two and anticipate before you measure as well. We want to connect the two worlds with 3D EM extraction and the measurement workflow. So this simulation design workflow is great to do that because we're starting in the same place. We're starting with the same rule of thumb estimations. And many times, the rule of thumb estimations actually comes from measurement. so we can really relate to the real world. Now next, before we go, I want to challenge you. I want to give you the cheat sheet, as I promised. The 5 rules that we have applied today, the 873 rule, the 0.1, 0.2 dB rule, single-ended rule for substrate height and width, differential impedance rule, and stub resonance. I want to challenge you today to anticipate before either you measure or you simulate. Because personally, I use actually 3, if not 4 out of these 5 rules every day. Every day with my cat. I will just talk to her, go over it, and just review how it actually works. So make sure you anticipate. If you see a trace that is 10-inch long, make sure you ask for the operating frequency or the data rate. Then number 2, you apply number 2, 0.1, 0.2 dB. Do a quick calculation. You will know what to expect for the loss at the Nyquist frequency. So make sure you today, before the end of the week, anticipate before you measure or you simulate. Finally, I want to give you all the signal integrity resources that I have. There is a signal integrity hands-on workshop that I have created with my colleagues here. Everything is packaged all together. We didn't go into too much detail on the simulation or how to work the software today, but it's all part of the hands-on workshop, which you can find here. Go to keysight.com//ads-si-workshop. There's also a YouTube video on how to solve signal integrity problems, where I apply the 3-step approach to solve any signal integrity problems. And make sure you download the latest ADS, apply for a free trial, and look at more videos on simulation and measurement over here on the SI resources. And all this will be available to you in the slides. And right now, I'm going to hand it back to Carmina.
Great. Thanks. Anticipate before you simulate. Got it. And measure. So let's see, Tim, what do we have coming in? Here is let's see. Here's a nice question from Uday, Tim. The pulse does not show reduction in amplitude after CTLE. Could you repeat?
Let's see. I can go back to the slides here, push to audience, and you see my slide right here.
Yeah.
So it does increase, but because if you look at the pink line at minus 0.5, it actually decreased to minus 0.3. So there's a decrease today due to a low frequency CTLE around minus 3 dB. That means it's going to decrease the overall I. But if you look at the gain here at close to 3 dB, it actually increased the peak. That's why also in the I diagram, we see that there's a little overshoot because we have a gain. Thank you, Dave.
Great. Here's a question from Sarush about the simulation of the differential T-line. What ports do we need to use an ADS, and what is the characteristic impedance? Is it odd mode or even mode?
Well, Sarush, the port we need to use is none, because the solver I use, it was a 2D field solver, and it will give you a very quick answer, an accurate answer, giving your 2D cross-section. But if you're asking the 3D solver, then that is a different, that we can talk that offline. But just based on what I use today, controlled impedance line designer, you don't have to specify the ports because it looks like the 2D cross section, the width and the substrate height. Based on that, it gives you the impedance, differential, and common, and make sure we know. Let's see, I see the odd or even. It gives you all the information, but what we really care about is differential impedance and common impedance for the differential pair. Thank you.
Great. Here's a question from Saish. I have also seen your video demo about the issue of via stub on eye closing and how backdrilling can result in opening the eye.
Very good point. Very good point. There are different ways you can explore the design solutions. As I can show you. See, I'll pull up the circle real quick. So your virtual prototype and 3D EM extraction. And thanks for bringing that up about back drilling. In the 3D EM environment, if your board has a via that you want to back drill, you can actually go in, right-click on the traces, and click back drill and the length you want to be, and you will see right away the dip is gone after back drilling. So that's one of the other solutions if you have money to spend on back drilling, that is. Thank you.
Great. And as a reminder, folks, we did put the demos that Tim was showing and the ones with the double audio into the resources widget, so you can download those anytime. Just press refresh. And some folks had asked about the recording. We are recording this. And Victor asks, this is very useful. Can you share the ADS workspace demo example put together for this virtual seminar?
Yes, and if you go to the SI workshop page, which can be accessed by keysight.com/find/ADS-SI-workshop. Everything is there. It goes into details on each component, which means you have the I diagram, you have TDR, you have mixed mode S parameter, and a single pulse response. It's all there out in the open. The video also gives you a good idea. So it's all there. It's all there, Victor. Thank you so much.
And here's a question that came from Garrett. You mentioned a lot about signal integrity, SI Pro. Does that mean I can also do power integrity simulations?
Yes, indeed. It's SI PI Pro. That means you can actually perform both signal integrity and power integrity simulation in the same workflow. After you import the board I'm showing here, this is a Xilinx board. Let me push to you. So the board has to have a power supply for it to work. It has transmitter, receiver coming and going. It has to have a power supply. If you were to be the engineer that's testing for the power supply and how the power distribution network were to work, SI-PI Pro is a great selection for you, because once you import the layout, everything is at your fingertips, all the way from SI to PI analysis on the same board. Thank you.
Great, thanks. And here's a question that comes from Alexis. When you import the board, does the substrate information come in too?
Yes. Given that you have BRD, ODB++, the Gerber, I'm not sure, but make sure, I always trust and verify. The substrate file, if you have BRD or ODB++, always comes in, but trust and verify. I always go in and verify the dielectric constant, and the dissipation factor is what I want, and the conductor loss, the conductor, usually I use copper, but if you have other material parameters on your board, you can go in and change it to your desired material properties. So the answer is yes. Thank you.
Great. And before we get on to some more questions, just a reminder to fill out the survey that's on the right hand of your screen of the slide deck. So the number of questions helps us get to know you a little bit better, helps us also figure out what other virtual events you want and what you also need help with. So go ahead and fill that out and click submit. All right, Tim, so let's move on to your next question. Okay. Had a little bit of college student running back and forth. Okay. So
your coworker.
Yes, exactly. So here's a question from Graham. How does the channel simulator work, and can I use my own S parameters?
Yes, the channel simulation works in this way. So first, it's going to take your S parameter and create an impulse response from it. And it's going to send in has different ones and zeros, this PRBS, pseudo-random binary sequence. It's going to convolve that binary sequence with your channel, and once it does that, it will generate an I. Now that is a bit-by-bit mode, but for applications such as DDR5 or applications requiring really low bit error ratio, down to 1e to the minus 16, we have a statistical mode, where a stochastic process is started in the background. It's going to do the similar thing, and get you down to 1 e to the minus 16. But to answer your question, yes, you can use your S parameter file to perform the channel simulation. Thank you.
Great. And let's take a couple more questions. So Anupama just asked, do we need AMI model for RxTX for the channel response?
Hey, thanks, Anupama. I think we met. Thanks for joining the webinar. You don't really need AMI models for the IX and TX for the channel response. But if you want to look at how realistic and how the channel will behave in a realistic situation, that is a great place to be. You have your IBUS model, input buffer specification information, and the AMI model, the interface for algorithm modeling. That'll be a great place to have, a great thing to have for, on the left you have a TX AMI, on the right you have your RX AMI, in the middle you have your channel. That is just a real great simulation to measurement workflow. That's as close as you can get.
Okay, and let's take this one last question and comment from Jan. Thanks, Tim. Very good presentation on the CTLE experiment. It's very clear that the eye opening improves after applying CTLE. However, what I don't understand is how CTLE helps jitter here.
All right, now to do that, let me go to that slide and then push to, right. So you should be seeing the loss curve right there and the single pulse response of the channel. And here's the cursor. So this is a quick review. And here's after CTLE. We see that horizontally, the timing does not really change, which means that CTLE doesn't really help us on the jitter, especially ISI jitter. But what it does do is, if you look at the minus here, it does take out some of the leakage from the main pulse. And that's how it's contributing. So if you look closely between the time 10.2 nanoseconds to 10.5, the width is the same. But what's coming afterwards is crucial. It's taking away that leakage ISI. So that's how it's helping the jitter. Not from shrinking the pulse width, but from taking away the leakage. Thank you, Jen.
Okay, great. So that's all the time that we have for questions today. Thank you again for attending today's event, Robust Design Workflow for Signal Integrity, brought to you by Keysight Technologies. Please visit us at www.keysight.com/find/events for a list of upcoming events. And stay well, everyone. Have a great day. Bye.